O futuro é guiado por dados, por decisões instantâneas, pela conectividade. E no sul de Minas Gerais, o Centro de Competência Embrapi Inatel em rede 5G e 6G, xGMobile, coloca o Brasil no protagonismo da nova era da tecnologia. Comunicação móvel que une setores, máquinas e pessoas. Soluções práticas para desafios reais. Quem lidera a transformação, cria oportunidades e amplia mercados. O futuro é agora. Ele começa em Minas e precisa de quem move a economia. Faça parte da revolução. Faça parte do xGMobile.
So welcome back to our workshop. We are starting now the afternoon section, and we start with the first technical section about the radio access network. During this section, we're going to count with 3 different researchers happening here at Inatel, at CPqD, at PUC Rio de Janeiro. The first one is going to be presented by Dr. Fuad Mousse Abinader Jr. He is the General Coordinator of the Competence Center on On-Prem at CPqD, and he will start to share us his challenges regarding this endeavor. Professor Fuad, please.
Thanks. Vou usar guia aqui. Thanks, Luciano, but unfortunately, I'm still no professor. I decided to go to the private sector, but thanks a lot. So, okay, it's working. So today, I decided to talk about AI run, so open and disaggregated networks and the evolution towards 6G. This connects very well with Professor Aiktis' talk this morning about AI run. I'm looking from the side of the infrastructure, how to make this work, and the challenges we face. So thanks again. My name is Fuad Abinader. I am Technical Coordinator of the Embrapi CPqD Excellence Center in Open Networks. So the second competence center that also look into connectivity in complementing what xGMobile does here with 5G and 6G. So yeah, and by the way, a disclaimer, I'll be talking about AI run. So I also ate my own dog food. So all the images, I am no designer. All the images I generated, we're also using AI as well. So that's just a disclaimer. So back to 6G. So to understand the transformations we are facing today, coming with 6G, I would say that we must recognize what I'm calling here the great convergence. We have 3 different, let's say, fields of knowledge that are connecting as we speak. So historically, the radio access network, the cloud infrastructure, and the artificial intelligence fields were like islands with their isolated knowledge that have been, as the technology evolving, they are being coming together and mixing, becoming what I'm calling here the same vector, okay? So from the run side, what was before an appliance that was purpose built, now it's becoming software that can be virtualized, okay, and can run in any computing platform. From the cloud infrastructure side, the dedicated hardware that you would acquire with Nokia, Ericsson, Huawei, and the like. Now you can use infrastructure that can be not only x86 general purpose computing, but also you can rent cloud infrastructure from public providers like AWS, Azure, and so on. And from the AI, what was over the top optimizations that you would do outside of the network, now they are integrating more and more with the network itself, becoming an intrinsic network capability, just like Professor described it earlier. So we are moving from this concept of simple connectivity to compute and connect, okay? In this architecture, I would say the base station is no longer just a repeater transducer or something like this. It is becoming effectively a GPU-accelerated edge data center. So this unification will allow us to move from a static 5G standalone systems to dynamic AI-native 6G. But before we reach there, we need what I call this deconstruct the monolith, okay? So we need to move from this paradigm where we have black boxes as the G node B to break it into different software components, okay? So because you cannot apply AI to a black box, you cannot optimize what you cannot touch, see, and control, okay? So for decades, the RAN was always a hardware monolith with a few parameters that you need to optimize. But if you want to make this AI native, we have to deconstruct, as I said, using disaggregation and virtualization. So for instance, right now, with 6G, you can use what we call the functional split 7.2x that separates the functions. For example, with 7.2x, you can have the radio part, the physical part here with the antenna, with the radio unit, and you can put the intelligence or the baseband processing split between the distributed unit and a centralized unit, okay? And that this already allow us to run baseband software on a standard custom off-the-shelf server, x86 or ARM, for example, just like any other cloud workload. This, for us, becomes strategic because by turning hardware into code, we can create a programmable platform. And this is the first enabler. Without this decomposition, there is simply no place for a radio intelligence layer to sit and no way for AI to control the network, okay? Unless you are Nokia, Ericsson, Huawei, and you are developing the software. But you as a network operator becomes complicated. So then comes what I described, another enabler, which is the Open RAN architecture, which extends 3GPP architecture for the network, introducing new interfaces, new components. So we have this division between CU and DU, which is already 3GPP, okay? And then we introduced a new subdivision of break the baseband processing in what is software part, let's say, the DU, and the hardware part, radio unit. Open front haul, something that I mentioned earlier. And then we have the different interfaces that come from 3GPP and additional new interfaces that are, for example, for allow the FCAPs to collect on the radio intelligent controller, which are new components that you add for different control cycles that you can create new algorithms, most probably built using AI and ML models that will collect information from the network and based on this information can train new models. Based on these models can apply policies that come and are in real time consuming metrics and then making decisions to update policies, okay? This architecture then complements the disaggregation that we discussed earlier, because now we have the mechanisms to collect information about the real state of the network and also modify the policies dynamically, okay? And then And then comes the third enabler, okay? This is what a new alliance proposed by NVIDIA, introduced a bit more than 1 year ago, called AI Run Alliance. And I tried to generate an image that kind of provides the vision, okay? So moving forward from last year, and then enters the AI Run Alliance. You might ask, why do we need another alliance, another SDO? We already have 3GPP. Now we have Run Alliance. Now you are talking about the third standardization SDO, AI Run Alliance. Well, the thing is, 3GPP is what we call the foundation, okay? They define the physics of the road. Imagine this like building a high-performance car. So 3GPP would be the foundation, define the physics of the road, the rules, basically the air interface, the protocols, and the way AI, and as well as the new AI study items we've released in 1920. Open RAN would be the wiring, the pummeling, providing the connectivity that allow us to collect the data and change the control. So without this, there is no data pipeline for the AI. But then we are missing the engine. So that's what AI Run Alliance is proposing. They are focusing on the implementation on silicon. While Open RAN would define how to connect, AI Run would ask, how do we effectively map a neural receiver into a GPU? So it's bridging the gap, this critical gap between the standard and the silicon. That's the vision of the AI Run Alliance, okay? And then we come to the 3 pillars of what they are proposing, AI Run Alliance. So the first pillar is more like what we understand as artificial intelligence applied to RAN, which is AI for RAN. So it's the use of artificial intelligence to optimize the network. We are more used to this, and this is the tradition. Here, idea is the optimization. So, okay, we are using machine learning, for instance, inside the stack to boost either spectral efficiency or energy efficiency. This is what will be, let's say, the traditional vision of artificial intelligence on the RAN. Then we have a second, let's say, use case, which is called AI on RAN, okay? The idea here is to increase the revenue. So you have this distributed platform, where now the would be traditional, the Genode B. And the idea is to use the RAN's edge footprint, the idea that you have some computing power over there, to host and monetize external artificial intelligence applications, okay? And that would allow you to generate new revenue. And then you have the third wheel, which will be a new one called AI and RAN. The idea here, the idea is to really build on the infrastructure. So dynamically, how to dynamically partition, for example, if I'm now making the edge computing platform that I'm going to share between the RAN and some edge applications, how can I partition this in an efficient way? Because they have very different nature. So AI workloads, they are more best effort for training, for instance, while the RAN workload, necessarily, it's more like time sensitive. So it's not just about optimizing the system, it's also about how to monetize and how to share this edge infrastructure, okay? So going a little bit deeper on this use cases, let's go back to the AI for RAN, which, as I said, it is more the traditional way, okay? So AI RAN is the answer, let's sort of say, to the overwhelming complexity of modern radio physics. I saw one time on statistics about the number of parameters to optimize the RAN in 2G. I read something about 200 parameters. And when we come to 5G, it's beyond 2,000. That's what I saw. I don't know if I never counted that, but it grows a lot. It grew a lot, the number of parameters to optimize the RAN. With massive MIMO, the number of parameters is simply too vast for traditional linear algorithms to handle efficiently, computationally speaking. We address this by replacing heuristics with data-driven inference. So first, spectral efficiency. We can use deep learning, for example, for beam management, creating sharper beams, to squeeze more bits per hertz, and things like this. And this morning, we had a lot of different use cases that go in this line, as well as on the energy efficiency. For example, instead of having rigid sleep timers, we can use micro sleep orchestration, by predicting traffic patterns. You could power down specific RF chains with chirurgical precision, things like this, okay? So essentially, we are shifting from a network that just reacts, just as Professor told this morning, to a one that predicts. So extracting more bits per watt from the existing hardware. Then comes the second use case, AI on-run. The idea is how to improve the monetization of the edge. If you are making the edge now not only exclusive for the RAN, we are sharing this with edge applications, then the issue is how to make it pay for itself. So the golden dream of operators, how to not become some not allow over-the-top applications to get all the money, to also monetize the infrastructure, okay? So technically, this is achieved through server consolidation. We can utilize the GPU-accelerated distributed units to co-host virtualized RAN components, stack and user applications as isolated containers, Kubernetes, for example, Kubernetes, on the same hardware. This solves, in a way, the challenge of what they call data gravity, where the data is. For a factory, for example, generating terabytes of 4K videos they use inside the manufacturing plant, backhauling that data to a central cloud is cost prohibitive, it's low. And even sometimes, the data pattern for the traffic itself already tells your competitors something about your business. So there's also security aspect of this. Also, by running inference, for example, locally, on the edge, we eliminate those ingress-egress costs and guarantee sub-millisecond latency for real-time control. What AI Run Alliance is claiming, that this is the Airbnb moment for telcos. So Airbnb is that service that I used, most of you have probably used, where you can get your apartment, your house, and rent for someone else for some specific period of time. So now they claim that we can transform the RAN into a multi-tenant edge cloud that can monetize ultra-low latency computing. And then comes the third use case, AI and RAN. It's all about efficiency, sweating the asset. So operators traditionally spend billions on hardware dimensioned for peak traffic, leaving expensive silicon idle most of the time, okay? So the idea is to solve this by treating the GPU as a fluid resource that you can allocate sometimes for the RAN, sometimes for the AI inference and things like this. But we must conquer a massive engineering challenge, okay? Because we have two opposing workloads competing for the same bare metal resource. So the RAN workload, for example, layer 1 baseband, requires deterministic and microsecond precision, so it's very time-sensitive workload. While the AI workloads, they are more tolerant, if it's talking about training, for example. It's computationally heavy, but it is best effort. And you can utilize technologies like GPU slicing or multi-instance GPU, where we can dynamically partition the silicon given the priorities for the different workloads. The RAN gets strict priority during the day, while, for instance, the way AI workloads can come and automatically fill every gap of unusual capacity at night. This, according to what AI Run Alliance sells, makes the base station become a jack of all trades. So it can be a radio by day and an AI supercomputer by night, okay? And the idea then you can ask yourself is, where can you use this in real? What are the use cases? So there are a few. The first one, for example, is for ISAC, Integrated Sensing and Communication, okay? So ISAC gives kind of a sixth sense to the network by converging radar and telecommunication into a single spectrum and hardware layer, okay? Historically, we treated reflections as noise, and with ISAC, we treat the same noise as prime intelligent information we can use. So by designing refined waveforms, we can reuse existing massive MIME infrastructure for passive sensing, so detecting objects purely by analyzing backscatter, for example. So we can have applications like in security, for example, an airport providing 6G coverage can use the same signal to also detect drone intrusions, things like this. Also industrial scenarios, you can use the backscattering to detect, for example, trepidations, micro vibrations, and trying to infer failures on machines even before they happen, things like this. All of this benefits from the AI workload that is processing the signal being collocated with the RAN software on the edge, okay? So this would allow to have radar as, for example. Then we have the another use cases that would be the AI native air interface. So this is, I'm already repeating the same idea, but just to provide here, we are transitioning from a model-driven to a data-driven field layer. So for more than 100 years, we have been relying on the rigid mathematical models that have been working just fine for us. But as the technology evolves and the requirements increase, these algorithms that we use to implement actually this struggle with real-world nonlinearities like power, amplified distortion, things like this. The idea is to propose to replace this with an AI native air interface using, for example, deep neural networks, autoencoders, that can create kind of a neural receiver, okay? Instead of fixed rules, it would learn to handle these distortions. The killer app, I would say, would be the pilotless transmission. This is overstatement, but it's more on the line that today we waste with 5G around 15% of the spectrum with the MRS and other pilots. Idea is that with a neural receiver, we would decrease. It wouldn't need all that much pilot. We will be able to regain a bit of the spectrum from the pilots to actual data transmission, okay? Again, this would also benefit from being collocated with the RAN and consuming the signals and doing processing on the edge, okay? And finally, a third case would be, for instance, semantic communications. The idea that instead of optimizing for bit accuracy, I would be optimizing for semantic fidelity. Think of this, for example, image recognition. Instead of transmitting the video or photo, I would just collect the features from my face and transmit way less information and reconstruct with a generative AI on the other side, things like this. This would also benefit from being collocated with the RAN, okay? So this is more or less coming to the conclusion, okay? More or less what will be the taxonomy for the research areas, okay? So on the first layer, we would have the air interface, where we would be worried about the receivers, what they call holographic, MIMO, pilotless transmissions, and so on. Then on a second layer, we would be looking into the control loop, the intelligence, RAN intelligence layer. So RF, XAP conflicts, for example, conflict mitigation, so yeah, and slicing dynamics, Isaac, things like this. On a third layer, we would have like the brain, let's say, serves an orchestration layer. So we would be worried about intent-based networking, multi-cloud orchestration, semantic communication. And on top of this, or better, on the side of this, we would have two verticals which are very important. So the security and trust, for example, worrying about adversarial machine learning, zero trust architecture, and so on, and also sustainability with so the carbon aware routing, AI for energy efficiency, and so on. Okay. Just to conclude, what we are doing working on this topic at XCOM, so the Competence Center in Open Networks, we are basically exploring this with automation or orchestration. So I will explain on Thursday what we are doing in terms of automation orchestration projects. We are already working on this, enabling multi-cloud, multi-tenant deployments. Also on the RAN intelligence and security side, enhancing security, for example, working with the distributed denial of attack on the initial access, the energy efficiency, dynamic sharing logic, and also vertical sustainability. So exploring different hardware platforms, using intelligence, and also how to use network intelligence to optimize for agricultural, connected agriculture, and for telemedicine scenarios, okay? So I invite you all to also be here on Thursday, where I'll be explaining a little bit more what we are working towards this, okay? And just to conclude, I don't know if you noticed the theme, like neon colors, inspired by the last jersey launched last week from Botafogo. So now you make the reference, yeah? So that was inspired by this. So anyway, thanks a lot for the opportunity, and that's all.
We do have time for questions. Yeah.
Thank you, Professor, for a good presentation. I have two questions. Is terahertz ultra massive MIMO can be deployable with AI-driven RAN? And other one is RIS can be co-optimized with AI RAN practically?
So just for me to understand, so you asked about whether we can implement massive MIMO with the AI run concept.
Yeah.
That's one. And the second one was?
RIS can be co-optimized with AI RAN practically.
I didn't get the first part, sorry.
RIS.
RIS.
Yeah.
RIS. Okay. Those could be two use cases for this. I have seen work both from NVIDIA and from universities using NVIDIA's platform with massive MIMO. I recall one working on RIS for processing, but more than specific algorithms, what I presented today is about the need to shift the way we build the infrastructure. Because if you want to take advantage of the edge resources, it is not just about putting a computer that the RAN we use together. To be more economic, to be more energy efficient, you need really to share. So you using ASICs for specific optimizations for the RAN is not efficient if you want to share the edge. Relying on GPU is a good approach, not the only one, but it's a good approach that would allow, in phases, needs to be proven, to be more economic efficient. So you can. I have seen works for both massive MIMO and RIS, but more than this, it's about if you want to have whatever application, Isaac or whatever, what will be the change we need to do on the architecture of the radio access network? I don't know if I answer you.
If we will increase the efficiency, energy efficiency, it is possible it decrease the quality of service.
Yeah.
It's possible.
Yeah, it is possible, and it becomes part. The ensuring the quality of experience becomes part of the multi objective problem that you need now to resolve. So whatever technique you need to use, you need to incorporate also this. It's part of the new multi-objective problem that you need to solve.
Actually, I was planning to ask you a question, but let me add something for this young fellow. So unfortunately, RIS is becoming an academic exercise. When you go to the mobile operators, they are staying away from it for the time being. And it's really responsibility of the academic world to help them to use the RIS for the actual deployments in the future. That's really sad, because I saw these cases that the academic exercises didn't make it to technology transfer. So there were many excellent ideas, but they became a publishing platform, and it didn't help to the mobile operators. But the ultramassive MIMO will definitely come.
Yep.
And also these surfaces that are talking about, like hologram type or active elements of these surfaces, they will help for the kind of like next generation of ultra-massive MIMO ideas. So very large number of elements, but active elements, that would be a good space for the 6G. So I hope I answered your question. And my question to you is, so when you go back to your, by the way, I loved your presentation. Fantastic. Bravo.
The theme.
No, the stack that you had before.
Yeah.
Not Botafogo.
I know you support Botafogo. You're totally yes.
Now the thing is, did I miss it? You didn't talk about network management, right? Did you? Because when you talk about it, then I missed this word, intelligent agents. They're running around in the edge, and so where are you placing them in your?
What we are exploring, for example, in our project, is the concept of this multi-domain optimization. So the idea is not to necessarily have multi-agent to solve the RAN, but to have this distributed, let's say, a federation of agents that working on the not only on the radio side, but also the data network side, working even on the energy source side. For example, talking to the smart grid to understand, adapt the way you are creating your baseband, the bandwidth. For example, if you are operating in isolated Amazon, and there's a lot of cloud coverage, so solar power is a problem. So you need to talk to the smart battery system to understand what is the load that I will be able to provide, adapt the range to that. So you would have different smart agents talk. So not necessarily within the RAN, but to talk with the other domains that you need to talk to coordinate to make things happen. I would say it's located more or less both on these two.
You mentioned here holographic MIMO. You see,
yeah.
That's exactly what I was mentioning.
Yeah.
And the dynamic slicing and multi-cloud orchestration, underneath you have all these agents, right?
Yep.
And semantic.
Yeah.
ISAC, it's right.
To me, it is yet still how we. That's why I asked you this morning, because I have a little bit of difficulty. If you really want to move from the static stack to a network of agents implementing this, maybe the way we build the standards need to change. So we might not stop standardizing headers in packets or how do we use the channel, but starting standardizing how the models will talk to each other. So MCP for the RAN, things like this. Maybe this is more important for the making your vision you proposed this morning to come than necessarily evolve in the air interface like we do since 2G, 3G, 4G, 5G. I have difficulty because it's like this, how we create this network of agents. I don't know if, but that's anyway. Your presentation this morning is a lot my work. Like, thank you.
Thank you, Fuad, for the presentation. Thank you very much. So now we can move towards the second presentation. I'd like to invite once again Professor Rodrigo de Lamare. He's going to talk about the hot topics on 6G wireless network.
Yeah.
That's right? Okay, so the floor is yours.
Thank you very much, Luciano. So this is the talk is entitled Hot Topics because that's what we are doing in my research group at the moment. So we thought that these topics could have an impact in terms of the training of the students and the postdoc researchers, and also some are supported by industry. So hopefully something will come into products in the future. Okay, so here's the outline of the presentation. The main topics I'm going to talk about are multiple antenna systems for 6G. So I've chosen the so-called extra-large MIMO systems, which are a natural evolution of massive MIMO. Some people call them ultra massive MIMO, or I'm going to call them extra large MIMO systems. I'm going to talk about them and the work we have been doing. Then I'm going to talk about reflective intelligent surfaces, also known as RIS. Okay, this is maybe a controversial topic by now because some people are reluctant to adopt that, etc. But there's a lot of potential. It's the #1 topic in wireless communications in the last 4 or 5 years, and it's amazing the number of papers on RIS. Of course, we now have quite a number of people also trying to demonstrate the feasibility in labs, in some basic deployments, etc. So I'm going to explore a little bit of RIS. Then I'm going to talk about semantic communications and what we have been doing with semantic communications. And then I'm going to wrap up with robust resource allocation, which is, I think, a very interesting topic because it deals with problems that we have of dealing with uncertainty in wireless communications. We never have perfect channel state information. This is something that only occurs in papers. Okay, so we should be prepared to deal with uncertainty by designing algorithms that take them into account. Okay, and then I'm going to wrap up in terms of conclusions and explain what we are currently doing and we plan to do in the near future. Okay. So, of course, they're all related to 6G wireless networks, and which will be deployed in 5 years or so, and will feature novel technologies and improvements. And key problems include the need for higher data rates required by new applications, talking about virtual reality, metaverse. Data centers are also a big thing, and lots of data centers are now being installed in Brazil, and they need communication, they need connectivity, they need energy efficiency, they need water and clean energy. So this is a big thing. And of course, and AI, of course, is requires a lot of connectivity as well, because now you're with AI, you can connect GPUs in a distributed fashion. They have to be connected somehow. So this is something that we might see. So another problem is the need for improved coverage of users' devices with poor channels. So one of the big challenges is if you are not so well placed in a geographic area, how can we improve this coverage? So this is a key problem that remains. Interference mitigation. So this is my own topic of my PhD, and this is after 20 years or so. This remains a very important topic because interference will remain something that impairs our networks, something that limits what we can achieve. So it's another key problem. And something that is now considered by a lot of people, something that came to as a problem, and also something we need to tackle is the sensing of users' devices and the combined use with communication. So this is almost certain that will be in 6G. So we need to we should tackle the sensing combined with communications problem. Okay, and this is through ISAC, the so-called integrated sensing and communications. And so I'm going to discuss these problems in this presentation. Okay. So of course I'm going to start with the extra large MIMO systems. And one of the interesting things about extra large MIMO systems is that we're going to have near field signal propagation. And this is something that wasn't considered in the past, and it's very practical, and it's a reality. Interestingly, I also have a signal processing background, and in signal processing, people have been dealing with, especially in array signal processing, People have been dealing with near field scenarios for a long time, but not in communications. And this is something that we see when you have users or devices very close to access points. So you have a near field condition or a scenario, and we should actually deal with that, try to exploit the situation. And it's something that extra large MIMO system will do. And we have to perform improved interference mitigation, and this might enable much higher data rates in 6G, not only because of the larger arrays, which can be distributed or not, but also because the near field devices, they will be exploited. Okay, so that we can do this wisely. So let's look at this. So we're going to talk a little bit about extra large MIMO systems, and we have this encompasses co-located MIMO systems where you have like a panel like this one, and it can be also sparsely located in a holographic surface or something like that. It can be modular like this, or it can be distributed. Okay. Many forms of extra large MIMO systems. But what will define them is the occurrence of these near field channels, where we have the so-called Rayleigh distance. It's one of the ways that we can classify the near field. And this near field is characterized by this Rayleigh distance, where here we have R is the distance, D, capital D is the array dimension, and lambda is the wavelength. So in these situations, we don't have planar waves impinging on an array. We actually have what we call the spherical wave propagation. Okay, and the spherical wave propagation is a bit different. So you have different channels or element, or let's say characteristics per element. Okay, you can have that, and also what we call spatial non-stationarity. And this is a very important property that we should take into account. So when dealing with extra large MIMO systems, we will have to tackle these things. And I'm going to show you an example of something we have done in the last couple of years, 2 years or so, that we have been working on this. And this is basically the work that I've done with Anzang Tang, because I trained many PhD students from China, and I continue to do that. This guy was co-supervised by myself. He's a student who graduated from Southeast University. Southeast University, you might have heard about it. It's one of the largest places for wireless communications in the world. It's a huge laboratory they have in all areas of communications. So I know his supervisor, so he invited me to be co-supervisor. So we wrote many nice papers on extra large MIMO systems. And this paper that we have here is called Joint Visibility Region and Channel Estimation for Extremely Large Scale MIMO Systems. So the main idea is to come up with a way that you can have a visibility region. So you have a part of the array that deals with a particular set of users only. So you have a huge array, and parts of the array will be responsible for certain users or certain groups of users. Okay, and this is what we call visibility region. Okay, we have some spatial non-stationarity there, and we do this, and we also do channel estimation. Okay, and so here's some examples of what we could achieve. We devise some algorithms that exploit this spatial non-stationarity and exploit aspects of this extra large MIMO system, such as the near field channels. So in this example, so we have a system with 256 antenna elements, which are co-located, okay, 60 gigahertz, okay, so it's a millimeter wave, which didn't work so well for 5G, but we hope that 6G it might be a bit different. And we have a pilot length of 45. Okay, so we're dealing with about 24 users here. We can deal with up to 45. And we came up with an algorithm that is called BBOMP. It's an algorithm that exploits sparsity at the level of the spatial non-stationarity, okay, and also exploits near-field scenarios, okay. And we compare. You see on the top curve there, we measure the normalized mean squared error against the SNR. And we have the worst approach is like a least squares based channel estimator. As you can see, the black curve is the very worst of them, and is quite far away from the others. The best one would be the Gini-aided estimator. It's the green one, and the proposed ones are using soft estimates and the hard estimates. These are the best, not far away from the optimum, the Gini-aided. So you can see that exploiting near field and spatial non-stationarity is a smart thing to do. So you get very accurate channel estimates, okay, which is a major step towards an effective extra large MIMO system. And here's another plot that shows the spectral efficiency in bits per hertz per second, okay, versus the SNR. As you can see, with this kind of channel estimator that exploits these features of extra large MIMO systems, you get pretty good performance. You see, the top curve is the perfect CSI. So that's the very best you can do. And with the proposed approach, the BBOMP algorithm, you get very close to the optimum. See? So I think this is a topic that is very promising. It's a very hot topic. And I would we're still working on that, okay? Because now we are bringing more channel codes for use with channel estimation and interference mitigation. So we have another student working on this, and we're going to also use distributed arrangements of extra large MIMO systems, okay? Right, so then the next topic is the RIS. So this is something I was a bit skeptical in the beginning of RIS because I thought it was like relaying to the 2.0. So like relaying the revenge, and something that didn't work so well, relaying, and a lot of effort has been put into relaying. And I initially thought that RIS could be the same. Then I had a student, and now I've got a postdoc on this, so they kind of convinced me that it might be worth a try. And so I'm going to talk about something we have done, which I hope might help, might make maybe some impact in the area. So in my view, RIS can play a big role if we manage to reduce its cost of deployment, and if we can show in practice with demonstrations that it can enhance the coverage and the data rates at sufficiently low cost. Okay, so this is my take. We one area of RIS that has been quite active is the architecture of the RIS. So we had the first passive, the active RIS, and then some people came up with the so-called beyond diagonal, and then the stacked RIS, the holographic architectures, and so on. There's a lot of electronics behind the RIS, okay? But all of them have a very similar problem. Channel estimation, it's very challenging when you have a RIS involved. It's a lot more challenging than a standard massive MIMO or extra large MIMO system. Why? Because what happens is the number of channel coefficients that you have to estimate it gets much worse because of the RIS. If you have, for example, multiple RIS, you start to have many channels. And then to estimate them, you go, for example, in this example, we go from M, is the number of antennas of a base station. Could be, say, M, without a RIS. And if you include a RIS or multiple RIS, you go from M to N times M plus M. So N would be the number of elements in the RIS. So this could be a disaster. So you see the number of channel coefficients, it just explodes. This could be a disaster, okay? So, so this is, when I started in this area, I thought, oh, why don't we try to solve this problem by coming up with something smart that can actually, you know, become practical at some point. So what is the idea? We realized that RIS also, 99% of the papers in RIS, they don't use channel codes, okay? Why is that if all communication systems, or virtually all communication systems, rely on channel codes, okay? So why is this the case? It's because a lot of people don't, they want to simplify the problem, or they don't have expertise, or they just haven't thought about that. So we decided to come up with an algorithms that use channel codes and exploit the channel codes to reduce this need for channel estimation. How is that possible? Because if you have sufficiently accurate estimates with very few pilots, you can use them to feed them back this information and continue to estimate the other coefficients, okay? And that's the idea. So you can still use very few parameters, or very few pilots, roughly proportional to the number of antenna elements, but you use the codes to help you by providing coarse estimates and then feeding back so you can estimate all the risk coefficients. So that's the idea, okay? And this is the scheme that implements that. The scheme gets coarse estimates, uses iterative processing with, for example, an LDPC code and LLRs exchanging, and then you start to refine the coarse channel estimates, which can be so-so, with the symbols that you have from your very few pilots. And I'm going to show you how this works. This is a paper that is going to appear now in Transactions and Communications. It's one of my PhD students, Roberto Porto. So he brought these things together. So channel coding and iterative processing can help with channel estimation and interference mitigation with RIS. So you can see here, a reduction of the number of required pilots is made possible by channel coding and iterative processing. And we also improve the interference mitigation. So in the top plot here, we are measuring the normalized mean squared error of these of channel estimation. So we have here a few plots here. This is the normalized mean squared error. Here's the BER with the channel codes. You can see that, for example, with the coarse estimate, that's the blue curves, that's pretty bad. When we start to bring the iterative processing that has this the number of iterations is beta. For beta equal to 1, you do one iteration, you see the change in the quality of your estimates of channels and the improvement in error rates. That's massive. Then beta equal to 2 iterations, and 3, you get pretty good channel estimates and with few pilots, okay, and pretty good error rates as well. And this PL would be the that we have here at the bottom. We have analytical curve. That's the best you can do. That's the optimal case, as the black one. And the green is when you have also perfect. Okay, all the pilots are there, and this is the best you can do. And another result we have here is this strategy is applicable to any risk, passive, active, beyond diagonal, what else, holographic. So any risk architecture can be used with this scheme. So it's broadly applicable, which is quite kind of interesting. So you can see here the benefits you have. A passive risk, of course, in blue. Then you have a beyond diagonal, which is a pretty strong one in red, and you have the so-called stacked risk in yellow. Okay. So the details are of course, in this paper. So the third topic I'm going to talk about is this knowledge-enhanced semantic communications. Okay, so we had a project with this paying is company that does paying machines. Brazil does kind of reasonably well with this paying technology. So we have a lab at PUC, which is a lab that in conjunction with Stone. Stone is the paying machines company. So they wanted us to study this kind of semantic communications for short communications with machines. Okay, and then we came up with this idea of using semantic communications that focuses on goals. So you have an image, or you have some kind of barcode, some QR code that means something to a machine. So you can use some machine learning that we call a semantic encoder that integrates knowledge, and then you transmit that over channel, and then you get a decoder that also is semantic, and then you get this data back. And we came up with something that uses graph neural networks, which are more powerful for this purpose than some other solutions, and we call this KENet. And this works very well because it does a multi-objective optimization with semantic, knowledge integration, and channel-aware loss components. So here is we trained this semantic communication system with a huge data set. This is one of the bad things about it. And we trained it, and we are measuring this criterion called BLE, which is basically the connection of words. This is for text. Okay, and we can see that the KENet is in green. So the higher the BLE against the SNR, the better. So when you have a BLE with a 1 gram, is basically you're focusing on a word only. When you have 2 gram, you have focusing connection to words, and so on. So you can see that the KENet does very well against other schemes. Just to give you an idea of the power of semantic communications, the bottom curve here, this is a 5 bits short code together with a turbo code. It does not perform well, you see? It's a huge loss for a traditional approach that transmits images or text, etc. So semantic communications in this context has a very can have a very high impact. Okay, that's very promising. So this is a paper of my student Hassan, and the results they indicate that all these papers here, Gen SC is from 2023 and Deep SC is from 2024. And the last one is about robust transmit processing. So this is what we call dealing with the reality in wireless networks. So we don't have perfect channel state information unless we are doing a simulation and in papers. Okay, in reality, we have imperfect channel state information. So we should design all the transmit processing at the base stations or access points, take into account that. So we should do pre-coding, power allocation, multi-user scheduling, all these resource allocation we can think about preferably should be done with the taking into account the imperfect channel state information. And this is what we are doing here. So in this approach that we are doing, we are using a worst case criterion that it comes from worst case optimization. Okay, this is something that exists for decades. Okay, and I'm going to show you some what happens when you have this kind of design. So here's a base station result for with 64 antenna elements, 16 users, and we have imperfect channel state information with this parameter alpha equal to 0.1. And I'm designing here a robust precoder with this approach, a robust power allocation, and a robust scheduler as well. Okay, and we can see here that the blue curve is the perfect channel state information. That's the best you can do. And very close to it, you have the red curve, which is the one that uses a robust scheduler, robust power allocation, and robust precoder. Very close, you can see. But in black, you have a very standard system. No robust precoding, no robust power allocation, and so on. So you see the difference from the black curve to the red curve. It's about 30% of gain that a robust design can offer you. And the cost is comparable. We're not talking about a much higher cost, okay? It's comparable. This is very appealing, has a big impact, can have a big impact on future networks, okay? So to conclude, so we discussed several 6G hot topics. We talked about channel estimation for extra large MIMO systems, RIS systems with iterative processing, semantic communications, and robust transmit processing techniques. I think all of them can be extended, can be changed, improved for future work, and we are actually doing that with the resources we have, of course. One of the things we are doing now is with this clustered cell-free designs with extra large MIMO systems. So there's a guy doing this, and extensions to multi-cell processing. We're also doing other interference mitigation techniques that exploit near-field scenarios. And we are working with semantic communications for machine-type communications. This is the STONE project. So we are collaborating with the company. And we're also doing now robust techniques, a special type of robust technique that we call distributionally robust technique. This is something that happens already. It's done. It's all well known in statistics, distributionally robust approaches. So we are applying that to robust transmit processing. So this is very, very interesting and very recent results we have. And I think this is, can be done by others, of course, in collaboration or on your own, okay? So this concludes my presentation.
We do have time for short questions.
Thank you, Professor, for a good presentation. I am curious to know about near field communication. You have mentioned, but I think in near field, the polarization is not clear. Mismatch of polarization. And can we use a linear polarization communication in near field, or we just focus on circular polarization in the extra large MIMO system you have mentioned?
So you're talking about the polarization, you see? So most systems use dual polarization. We are not taking this into account here, okay? I know there are some studies, but we haven't taken this into account. So our focus was really to look at the spatial non-stationarity and the near field scenarios and exploit some sparsity there in these domains. You see, we haven't looked into polarization.
Because I think in extra large MIMO, there is maximum chance of mutual coupling. How we can reduce this effect?
A mutual coupling?
Yeah.
Okay, that's an excellent question. So mutual coupling, it's something that really affects most of these systems that have antenna arrays. And the trouble with mutual coupling is that the coupling itself depends a lot. It's time varying, depends on the users, how the signals impinge on arrays and so on. To deal with that, you can model the mutual coupling, okay, and use algorithms to try to mitigate the effect. That's one thing you can do. But also from an electromagnetic point of view, you can take into account the array geometry. There is a set of arrays called sparse arrays that they are built, take into account the minimization of mutual coupling, okay? So if you look at sparse arrays, you can place some of the sensor elements farther away from each other, and this minimizes mutual coupling, okay? And you can, for example, look into the geometry, can look at the algorithms to model and mitigate mutual coupling and so on. So this is how I would approach this.
All right.
Okay.
Thank you.
Okay, let's thank you for Professor Rodrigo once again. Thank you, Professor.
Thank you.
Okay, so our next talking will be divided by Professor Felipe Figueiredo, which is a professor here at Inatel, responsible for the Y Lab, and also by Professor Rausley, that works with here at Inatel. The presentation will be started by Professor Felipe and then immediately transfer to Professor Rausley. Professor Felipe, the floor is yours.
Thank you, Professor. Good afternoon. My name is Felipe, and together with Professor Rausley, we will be presenting our work, Unlocking Vehicular Communication with Fluid Antennas and Deep Learning. This work focuses, as you can see by the title, mainly on the use of fluid antennas, that it's a novel concept I will try to explain a bit about, and deep learning to improve vehicular communications. De baixo. So this is the agenda we will be following here today. First, I will introduce some concepts about fast fluid antenna systems. Next, I will move on to the IEEE 802.11p standard, some concepts about it. The problem related to the high power amplifier, that's something we also are dealing with, and where we can apply deep learning in our work. Our two proposals with the system model, and then I will pass the token to Professor Rausley that will be presenting our results. So let's start with the fluid antenna systems. So these fluid antennas I have been talking about a bit. I don't know if you are aware of this, but they mostly enable, as I say here, a single physical antenna to behave like many virtual antennas distributed along what we call an aperture of length W lambda. So you can think of physical antenna as a wire, but it's split into small parts that we can move instead of having many antennas and RF chains, as in a MIMO system. We move the effective radiation point, the receiving or transmitting point, across the different positions, what we call the ports in our work. So one or a small subset of ports can be activated at a time. So depending on the cost, we can activate more than one, but basically we work with one port, and sometimes we can activate more than one to have a maximum ratio combining, for example, and we can activate and harvest. That's the most important part, spatial diversity at a very low cost. So we don't need to deploy antennas, RF front ends. We just need, for example, one RF front end, and we just switch, move the effective radiation point. So the design parameters we are dealing with here in this work are the aperture size, the length, the number of ports, the number of, we can also think of pixelated antennas. It's a concept similar. The number of ports, as I said before, the port spacing is also a parameter we try to deal with. The switching latency, it's very important, and the spatial correlation, because these ports are very close to each other, so we have spatial correlation that we normally are modeling with the JX model. So why these fluid antennas matter for vehicle to anything? That's V2X. So So these vehicular channels, I think you all know or are aware of, they change very rapidly due to the deep fades and everything that occurred at a sub-wavelength distance, mainly due to high mobility and multipath. So what FAST performs in our case, it's a spatial sampling of the channel response. So we can, by doing this spatial sampling, dynamically select the port, giving us the highest instantaneous SNR. So you think of all those ports, and we can look, we can measure the SNR at all those ports and select the one giving us the highest SNR. So with only one port is activated at a time, we can minimize both hardware complexity and cost as well. So it's a contrast to conventional MIMO systems, especially massive MIMO systems where we have lots of antennas and RF chains. We can achieve, instead, in contrast to a conventional MIMO system, we can achieve spatial diversity through motion of this radiation point. So the main general idea here is that instead of having lots of antennas, lots of RF chains, we just move the radiation point along this single antenna. So we just change the position we are receiving or transmitting our signal from. So let's introduce a bit about the IEEE 800 2.11p air interface. So the interface is quite simple for this standard. It's a well-known standard that enables vehicular communication. It operates at 5.9 gigahertz with a bandwidth of 10 megahertz, which is narrower than some versions of Wi-Fi, ANG, more specifically. It employs the OFDM modulation with 64 subcarriers, where 52 are active subcarriers. The other ones are left for guard bands. Out of these 52 subcarriers, 48 are used for carrying data and for transmitting pilots. Its frame starts with a preamble. Each preamble contains one short and two long training symbols that are used for synchronization, carrier frequency offset, and channel estimation. This preamble section is followed by a signal and a data sections, as you can see here in the figure. And why this frame structure matters to, as we will see next, for this fluid antenna system. Because the preamble, it enables us to get an initial least squares estimation across all fast ports, if it's necessary. We will see next that's not the case in our proposal, but it enables us to have this initial estimate of the channels. And the data section, it enables us to improve the channel estimates using what we call data pilot aided DPA method. Let's see a bit about the high power amplifier problem, that it has to do with the distortions we have from these kind of amplifiers. So as we all may know, the high power, the problem with the high PAPR, the power to average power ratio in OFDM, they drive the amplifier to work in what we call its non-linear region. So it causes some problems like amplitude to amplitude and amplitude to phase distortions. And in most cases, to reduce the effect of this kind of non-linearities, the power amplifier, it operates at we call a given input back off, IBO, from the 1 dB compression point. So it's some kind of trades efficiency for linearity. We also model in our work here the distorted HPA's output, what we called here UN, with the Busgain decomposition, where XN is the input to this power amplifier. Gamma 0 is a complex gain. Delta tilde N is uncorrelated, nonlinear distortion. And the takeaway message here is that the channel estimation must remain robust to these non-linear distortions, even though it impacts both the pilots and also the data subcarriers. Next, let's see where we can apply deep learning to our work. So just a small reminder, a brief reminder about what is deep learning. It's a sub-area, as you guys might already know. It's a sub-area of machine learning that uses neural networks with dozens or hundreds or even more layers. It can learn, in our case, we are focusing on our work here. It can learn the complex nonlinear mappings from the data itself. So unlike, totally different from traditional algorithms, these deep learning models, they can learn directly from the raw feature. So no feature engineering is needed here. So no manual design of features like channel statistics or the model is required. We just need the raw features in our case. So some typical deep learning architectures that you might see around is one of them, the most well-known one, is the dense neural networks. That is a standard fully connected networks for general pattern recognition, also regression. The convolution neural networks that are able to learn spatial and frequency domain features, used mostly in computer vision problems. The recurrent neural networks, the most prominent one are the LSTM, the long short-term memory based networks that have memory and they can learn temporal correlations that are used for time series, dealing with time series. And the goal here is to find a model that generalizes across these different channel conditions and also the distortion patterns we might find with the high power amplifier and also some mismatches with the hardware. So why deep learning helps in wireless communications? So as it's a well-known issue, these traditional estimators like the least squares, the linear minimum square error estimators, they assume linear models and stationary noise as well. So the problem is that in practice, these fast V2X channels, they are totally nonlinear, time varying, and spatially correlated. So in our case, to solve these problems, the deep learning models, they can learn these nonlinear distortion patterns from the HPA, the high power amplifier, and also from any kind of hardware mismatch we might have in the transmitter or on the receiving chain. It also can learn the temporal evolution of the channel and also spatial correlation across all the ports we have in the fluid antenna system, and as well, mapping from distorted pilots and data subcarriers into cleaner channel estimates. So the benefits in this case are that these deep learning based models, estimators in our case, can achieve lower error, for example, bit error rate, and they also have a better detection performance in mobility and nonlinear regimes than the linear estimators I mentioned before. So where can we apply these deep learning models in our work in this fast V2X communications? So we can insert this kind of models at any different points in the communication system. I have some examples here. So we might have deep learning at the receiver to predict, as I will mention next, the best fast port without evaluating all the ports, because there is an issue related to evaluating, computing the SNR throughout all the ports. We can also use it to refine the least squares and DPA channel estimates. At the transmitter, we can learn power control and also beamform decisions from the historical or statistical channel state information. At cross-layer use, we can predict the reliability and schedule port switching to reduce latency. That's a very important use. But in our case, in this work, we will focus on receiver-side deep learning for the best port prediction and also to refine the channel estimates. Next, I will introduce our proposal that is split into, in fact, into two proposals. But first, I will talk about a bit the system model. We consider a single antenna transmitter, of course, employing the IEEE 802 11P standard, which employs OFDM as its modulation. We also consider as impairment the high power amplifier nonlinear distortions, as I mentioned before. At the receiver side, we use a FAS, a fluid antenna system with 100 antennas. The channel, we are using the frequency selective Rayleigh fading as our model, and for correlation, we use the Jakes model. Here I present the estimation flow that in our case with the fluid antennas, it consists of three main steps. The first one is the least squares estimation per port. So we use those training symbols I presented before from the preamble to get an initial least squares estimate for each port, as I mentioned earlier. Next comes the port selection. So we use those estimates to select the port, giving us the highest SNR for the data reception. So we receive the signal through that port, giving us the highest signal to noise ratio. And then we can perform the data pilot aided update symbol by symbol. It is done, it's carried out symbol by symbol using the selected port. So we use the decoded data from the frame structure. That's why I presented the IEEE 802.11p frame structure, because we use the decoded data symbol to update the channel estimate for the next symbol. So we have a small improvement, but there is some problems related to this DPA update, as I mentioned here, because these estimates, they degrade quite quickly under high mobility, especially due to the error propagation we have across the OFDM symbols, and also because of the distortion imposed by the HPA. So our first proposal is using deep learning for port prediction. So the problem here, as you may already understood before, as I was talking about, the computing the SNR for all the ports is basically, if we have to evaluate the SNR at all the 100 ports, it creates a very huge overhead and also increases the latency of the communication system. So our solution is to use deep learning models to predict the best port from all the N ports we have, but just observing a small fraction of the ports, a small subset we called N capital observed ports. So the workflow is like is shown here. We have as input these SNR values from this small subset of ports, of course, a number small than 100, and as output, we have the predicted index of the best port, a number ranging from 1 to 100. So in this case, our deep learning model, it learns the spatial correlations across all the ports and use that information to predict the SNR at all ports so that we can select the one giving us the highest value. So our goal here with this first proposal is to optimize, to maximize the bit error rate performance by receiving the signal, the transmitted signal through the port, giving us the highest SNR. The second proposal is using, in this case, employing deep learning as a channel estimate refiner. The problem, as I also mentioned earlier, is that the DPA-based, the data pilot aided based estimates, they degrade quickly. Yeah? They get old very quickly because of the high mobility and also because of the high power amplifier distortions. So our solution to mitigate this problem is to use the DPA estimates we have based on the least square estimates we get from the preambles as inputs to a deep learning model, which will refine the estimates. So the workflow we have is shown here. We have the coarse DPA estimates based on the least squares. It goes through our deep learning model, a trained model to refine, to improve, to remove noise, to learn how to unstore the signal, and then we have the improved channel estimate as its output. So in this case, this is another deep learning model. It's not the same as the one we use for selecting the best port. So this model learns these nonlinear patterns from the HPA and also this time varying statistics from the channel that normally in general these analytical models like the least squares, the minimum mean square error estimators, they don't get. So in our work, we assess both models, deep neural networks, the dense neural networks, and also the recurrent one, in this case, the long short-term memory model for the task of refining these channel estimates. So now I pass the token to Professor Rausley that will be presenting the results we achieved in our work. Thank you.
Good afternoon, all. Let's move to some results of what Felipe said about actually two tasks. The first one is about the estimation problem, and the second one is about the port selection problem, or the port prediction problem. Here we show the system setup. We have a fast system with 100 ports. This port use the JX correlation model that is very common. We use three different velocity, a low 50, medium 100 and 200 kilometers per hour in our simulation. We include an input backoff of 4 dB with 16 QAM modulation. We compare actually the traditional DPA that is used, and the DPA refined by the dense neural network, the second one, and the traditional DPA refined by the LSTM model. All the estimation is a symbol by symbol estimation, is not a frame estimation, but a symbol by symbol estimation. Then you have here the common training parameters in the deep learning task, and also the model architecture of the deep learning system. The first result is the normalized mean square error as a function of the signal to noise ratio. We have the three estimation techniques. We also evaluate a single antenna system and a multiple antenna system, actually one antenna with 100 ports, just one receiver, not a lot of receiver, but just one receiver. And we have here the top curves are related with LSTM. This top curves achieves the lower normalized mean square error that we expected in the beginning of the process when we started this study. And the top curves are related with the traditional data pilot aided system or data pilot aided estimation problem. We have the best performance in terms of estimation, both across the 50 kilometers per hour and 100 kilometers per hour. Then we could prove that this estimation technique by using deep learning system, it's good in terms of we could refine the estimation of the data pilot aided. And the normalized mean square error don't tell the full story of the performance of the system. We need to evaluate also the bit error rate. Here we have the curves, the bit error rate as a function of the signal to noise ratio across 50 and 100 kilometers per hour. We evaluate the single antenna scenario and the use of the FAS with 100 ports. Actually, we have 100 ports, but we estimate the SNR of all ports, and we just choose one port with the highest SNR in this specific scenario. We have the curves, the bit error rate relate with the perfect channel estimation, perfect channel state information. Then we have these curves for the single antenna and for the single antenna here, the solid line, and for the FAS, the dashed line. But also we can see the DPA refined by LSTM. We have an excellent performance close to the single antenna one for both, for 50 kilometers per hour and 100 kilometers per hour. Actually, we have decided because of the reviewers asked to improve the velocity of the environment in general, we put 200 kilometers per hour. In this scenario, we have the increasing of the bit error rate in terms of the bit error rate. And it's obvious the performance degrades due to the high Doppler shifts and also the data pilot aided error propagation. We can see in these curves. Then in this scenario, we change a little bit. We evaluate the single antenna. We evaluate the one port FAS, 100 ports, but we just select the highest SNR. But we also use a two-port maximum ratio combining together with the FAS system. That is, we have 100 ports, and we select the two best ports, and we combine these two ports using the maximum ratio combining. Then, in this scenario, the best performance is the maximum ratio combined because we combine two ports in this FAS system. And one of maybe the most important result in this work is about the port prediction. We have 100 ports, but the idea or the question is how many ports or how few ports can we observe and we can predict the other ports. Then, for example, in this point, we just observed 15 ports, and the others 85 ports, we predict the channel of these ports, the coefficient of the channels. That is a prediction. Then we can see here, well, this is the port prediction model that we use. Actually, we use this because there is a high correlation value between the ports because the size of the antenna usually is too small. Then we have a high correlation. We take into account this characteristic. Then in this scenario, for example, we have a perfect channel, full knowledge of the 100 ports is this line here, this dot line. And here we have the observed ports. For example, for 15 ports, the performance is almost the same here. And we have the perfect channel only with any observed ports is this curve, this one. And the DPA refined by LSTM, I think this is the best results, the practical results. We have this green line. Then our LSTM-based predictor achieves near full knowledge, bit error rate, just by observing around 15 ports in this specific scenario. We have already studied a little bit about complexity. Here, the complexity is analyzed per symbol. The data pilot aided the order is about the order is related with the number of subcares, proportional to the number of subcares. Obviously, when we use some kind of deep learning system, the complexity increases. And here, the DPA refined by dense neural networks, the order is also proportional to the number of subcares, but also the number of observed ports. And the greater complexity is when we use the LSTM because of the natural recurrent nature of the LSTM system. Well, in the design, in terms of design levers, the idea is to reduce the N observed via some kind of port prediction that we used here. We use of lightweight models like liquid neural networks and some trade between normalized mean square errors and bit error rates, also bit error rates, and latency, obviously. Well, some conclusion of this work, we have been working these projects this year. We are trying to implement some real models. For example, we use the Jake's model, but we know there are a lot of different models for the channel, but we use maybe the simplest one. The combination of fluid antenna system, also sometimes called movable antennas, plus deep learning estimator are a robust solution for IEEE 8011P standard under mobility and with high power nonlinearities. The proposed workflow that Felipe showed successfully reduce both estimation errors in terms of normalized mean square error and system overhead when we implement the port prediction. For future work, we intend to implement a joint learning of the port selection and channel estimation because the task today is implemented in different parts of the system. The exploration of other lightweight models like liquid neural networks on device computing for device computing in the edge, and application to newer standards because we have used the 802.11p standard. Thank you.
Questions? I do have one. Regarding the standard, perhaps Felipe could also join. Felipe, can you join here? So, but my question is regarding the standard, right? I understand the motivation for using 802 standard because of the car communication, V2X communication. It's a quite usual. But also I see that 5G is evolving to cover this scenario. Are you considering also to include 5G, for example, RedCap, as one of possibilities for this study?
Not really right now, because our motivation was related with vehicular communication, and we had a PhD student previously working with vehicular communication, and the idea was to implement this port prediction in the environment of fluid antenna system in the vehicular communication scenario. But I think it's perfectly possible to implement this kind of phase and port prediction, chain estimation in the 5G standard.
Yeah, I agree. If we have the pilots, enough pilots to estimate the channels at least for 5, 10, or 15 ports, it's doable. I think so. Yeah. It's all a matter of changing the standard.
So it's agnostic to the standard.
Yeah.
At the end.
Yeah,
Okay, that's
sure.
very good. Other questions?
So thank you for that. I have a curiosity on this 802.11p because you were mentioning this scenario of mobility. Maybe mobility is because you use a specific channel to consider mobility, or you consider also Hanover. Is 802.11p considering that scenario?
As far as I know, I don't think so. But I'm not totally sure about that. We have to check. It might. I think the standard might somehow handle that. I'm not sure.
It was a curiosity only
Because it's a good question.
Usually mobility, the main issue in mobility when you are doing Hanover. So that's why I'm curious how Wi-Fi is handling that type of problems. Huh? So, but I have another curiosity also about the latency, inference latency. Can you share with us what could be a requirement from inference latency based on this technology?
It will mostly depend on the coherence time.
Mm-hmm.
Depending on the coherence time, if it's too short, it might be very fast. I mean, the time to switch between the ports and estimate the channel, it takes. That's why we are employing deep learning to shrink the number of ports we need to read.
Yeah, I was asking you this because this is a common question in standardization. There are many solutions based on AML, but inference latency plays a key role.
Yeah.
Usually it's related to the frame structure also, how long it takes. The minimum, it's up to the application.
Yeah.
But okay, I was curious how you are handling in Wi-Fi. Huh? But that's all. Thank you, Felipe. Thank you, Jose.
Welcome. Just one observation. When you observe, for example, 15 ports instead of 100 ports, the idea is to try to diminish this kind of problem, latency, not to have to estimate 100 ports, but just a small number of ports. This is one of idea of latency in this context.
It means
I agree with you.
reducing time to take the decision where the port is.
Yeah. Sure.
Imagine having to compute channel estimates throughout all the 100 ports.
Yeah.
How long would it take?
Yes.
Yeah, that was a good contribution. That was a good point. Another suggestion also based on discussions that we have in 6G now in 3GPP, it's about the pilots. Usually, I'm not sure if the pilots are using the same waveform than the resource elements used for data. So usually the impact of the power amplifier is different.
Yeah.
Maybe you can consider in the further study also.
Yes.
That's a nice topic.
Yeah, sure.
Yep. That's all. Thank you.
Welcome.
More questions? Just a second, please.
Why you choose 50 rounded and 200 velocity to evaluation your proposal?
Yeah, the idea was just to have a low, medium, and high velocity scenario And also, in order to show the results, I think it's important to have different kind of velocity, but we have some kind of restriction in terms of to publish, for example, a paper when we just choose these values. It's not a specific reason for
regarding the number of ports. It's because it's the number that gives us the best result.
Yeah.
More questions? Okay, so let's thank you, Professor Rausley and Felipe once again. Thank you.